Thank you very much. It's not an easy task to talk about the Frank works. I had to make some choices we are going to discuss, but let's play a game. So if you want, you can take a piece of paper. Nobody's taking a piece of paper? Come on. And write down your 3 favorite papers of Frank. Let's see if they coincide with mine. If there is a coincidence, I will give a prize tonight. But anyway, so before starting talking about his papers, let's just do a brief overview of his career. He was born on 26 December 1965 in Harfleur, France. I looked very hard for a picture of Frank at that time, as a young boy. And after a lot of work, I could find one. I hesitated. I was not sure that was really a picture of you. But then, when I saw the red pencil in his hand, I was sure it's him. So that's where he was born. And then he came to do a doctoral teaching, as a doctoral teaching assistant in Rennes from 91 to 94. He moved to Lille in 94 to 2006, where he was a CNRS chargé de recherche, first in Lille and then back in Rennes. And he was promoted to first class in 98. And then, as all of us, he started to become, he moved to Barcelona also. And as all of us, he started to start a little bit older. So he became a CNRS research scientist in 2006. And since 2015, became a DR1, and 2022, exceptional class. Very good. So these were his positions, but he studied most of the time in Rennes, all the time in Rennes, essentially, right? So licence, maîtrise, the master, elliptic curves with Montreal. I didn't know that. I was surprised by this. And he did a PhD thesis on singularité de feuilletage holomorphe à holonomie résoluble with Dominique Cerveau, 94, and HDR in 2000 sur la structure transverse d'une équation différentielle ordinaire du premier ordre dans les domaines complexes. Oops. Very good. He gave several talks in very important places. Probably the most important place was here at IMPA. Just kidding. But he had several participations in Brazilian Mathematical Colloquium. He gave a plenary talk in 31 Colloquium. I don't remember exactly the year. Do you remember? I don't. But he gave a plenary talk then, and very recently he wrote a book for the last, prior to last Brazilian Mathematical Colloquium, where you can learn about the geometry of Painlevé equations. So he had lots and lots of PhD students. The first one is here with us, David Marin, in 2001. But then there was Teyssier in 2003. After that, Victoria in 2008, Karamoko Diarra in 2011, Gaël Cousin 2012, Arnaud Girand 2016, Olivier Ton, also here with us, 2017, Nestor 2018, Aham 2019, 4 in a row. Wow. Jesus 2020, 5 in a row. Chito, and then he got lazy and it took 2 years to graduate of another one. Chito in 2022. And he's currently advising Gibran and Mattia Morbello. Gibran Ramos and Mattia Morbello. He published a lot, 60 papers, at least 3 books, and published in several important journals. And has a lot of co-authors. You see, I am proud the co-author of 11 of his papers. I think it's more, but anyway. And here where you see how he's getting obsessed with publishing. He's publishing a lot lately. Huh? We should be careful. He's publishing really, really a lot. And it was very hard to choose topics to talk about. This is a word cloud of all the titles of his papers. You see that there are a lot of foliations, there is a lot of projective, a lot of curves, singular, neighborhoods, and so on. But I had to choose only 3 papers. They are not the most important. There are papers that at some point in my life, I spent a lot of time of them for different reasons. Either I want to generalize, or I wanted to learn something, or I just found it really, really nice. And I will try to discuss these papers, give some context to them. And please, I haven't prepared this very well, so I might miss a few arguments. So Frank already accepted to help me, but you also can help me, because I'm sure that I was not the only one to have read the 3 papers that I will discuss. Any guess what the first paper would be? Daniel? Wild guess. Let's see if you... I will put the 3 in chronological order. So, close. I thought about that one, but no. So the first one has this very, Frank already know the paper, but has this very curious sentence in the Mathematical Reviews by Yakovenko. The title and place of publication of this elegant instructive paper may be somewhat misleading. This is to put mildly. I'm very envious of this paper because he managed to publish it in Journal of Number Theory. Can you imagine Frank doing Journal of Number? Has nothing to do with number theory, but he managed to do that. This kind of project of my life is to do the same. So this is the first paper that I want to discuss. It's un théorème de Frobenius singulière via l'arithmétique élémentaire. So I think you did that a few years after your thesis, right? It's not one of the Fates paper, 98. It has relation with I think it's somehow, the examples that they gave, I had the feeling that come from he's working on this cusp singularities, but here the problem is different. It's criteria for existence of local first integrals for a germ of codimension 1 foliation. Okay? So you have a germ of codimension 1 foliation on Cn, n at least 3. And they gave a criteria, it's a joint paper with Dominique. They gave a criteria for the existence of first integrals for these objects. So perhaps I can state the theorem. So the theorem is this one. Let F be a non-dicritic foliation on Cn, codimension 1, and suppose that the tangent cone of the foliation is reducible of degree nu plus 1, where nu plus 1 is a power of a prime number. Then you have a first integral. So what's the tangent cone? We already talked about this tangent cone. So we are considering a germ of one form, and so we can write it in homogeneous components. They're homogeneous components. Oh, let's put nu to keep the same notation. You can do this. And the tangent cone of F, so this is on Cn 0. And the tangent cone of F is the curve, I can think of the tangent cone as something contained in the exceptional divisor, which is just a p n minus 1. And this is something of degree nu plus 1 for 0. And it's just a curve on a hypersurface, a divisor on yn plus 1. Okay? And so he's assuming that the foliation is non-dicritical, meaning that the resolution of singularity, of reduction of singularity, has no what? Non-invariant component, non-invariant exceptional divisor. All exceptional divisor are invariant. All reducible components of the exceptional invariant are invariant of the exceptional divisor. And he's assuming that the degree, that nu plus 1, is a power of a prime number. Okay? So to put in context this result, you have to compare, of course, with one result that's very found to all of us is Malgrange theorem, which puts an assumption for the condition for the existence of first integral, asking for the singular set to have codimension at least 3. So this gives automatically a first integral. But perhaps even more importantly is Mattei-Musil theorem, which gives a topological criteria for the existence of holomorphic first integrals, and also a lot of study related to the holonomy and so on. We also can think about, if you start to assume that you have non-dicriticalness and that the tangent cone is smooth and so on, you have also the results of Fulton that says that the fundamental group of the complement of this thing will be a finite group, so finite holonomy, so holomorphic first integrals. We had all these ideas. But you see, they put an assumption of arithmetic nature. They are asking this to be irreducible of this degree, for prime degree or power of a prime number. But they are giving no assumption whatsoever on the nature of singularities of these objects. So here in my picture, you can see I put a lot of nodes as singularities, but it could have worse than node singularities. There is no assumption at all at the singularities of this curve. So even if the homology of the complements is simple, will be cyclic of this order, the fundamental group can be very, very, very complicated. So here we see, we can think of this, all the problem already lies in C3. So I did this drawing and thinking of this, the cone on C2. And what we are going to do is kind of strange thing. What they do to prove the result is that you have this fundamental group of the complement of a curve, which has a lot of structure, a lot of beautiful results. As I was saying, there is Fulton, there is this, there is that, which gives a lot of structure that you could try to exploit, but they will forget this structure. They will pass to take a line here, intersecting the curve transversally, and they will try to analyze what is happening here along this line. They will try to compute the holonomy of the foliation along this line. And to do that, you get a representation of P1 minus a bunch of points, whose fundamental group is just a free group, a mass, no relation at all. We forget all the structure, but still, that's how they will proceed. Because what they are able to show is that the holonomy, the holonomy maps, they can, since they come from this irreducibility of the curve, allows them to control the multiplicative factor, the linear part. They know who the linear part is. And at the top of that, the irreducibility of the curve implies that all these maps, all these generators of this free group are conjugated. So it's not any group, even if now we have a representation of the free group, is a very special one, where you control the linear part, and you know that any two elements, any two generators are conjugated. And they can prove, they transform the problem, the geometric problem, a problem about these holonomy groups. And they can prove that with these assumptions, this group, a group of diff C0, with the same linear part and linear part 2 pi exponential of 2 pi I over a power of a prime number, 2 by 2 conjugated, and then the group generated by these things is a finite group. Very nice, very, very beautiful. And you see, this is one of characteristics of the work, a lot of works of Frank, where you really transform a geometric problem into a problem about the holonomy and prove nice things from that. Okay? So that's what the first paper. I really like this paper. It's a very, the result is very clean. The proof is a short paper. I invite all the students, everybody who is interested, to take a look. It's a very beautiful written short paper where you learn a few things by reading it. Okay? Okay, so I will move to the second paper now, I guess. Any guess what would be the second paper? It's in chronological order. He's very good, but he did that after his PhD thesis, so. No? So the second paper, this is a part of acknowledgements. Most of this work has been carried out during a visit of the first author to IMPA and a visit of the second author to the Université of Lille. I think some in the audience already guessed which paper it is. But it's a paper with Júlio, which is minimal rigid foliations by curves on Pn. I think I read this paper. I spent a lot of time of this paper because a work I was doing with Paulo Sad, and also had some influence in a work that I later done with Collier Coutinho. But it's a paper that I find really, really, really good. And it's a paper that has a lot of characteristics that really impressed me. So it's, again, a beautiful interplay between pseudo-groups and dynamics, local dynamics, dynamics of groups of diffeomorphisms, of pseudo-group diffeomorphisms, and global geometry of foliations. And it also has a venerable history. While the previous paper had this influence of the work of Malgrange and Mattei-Mussur, I think this paper owns a lot to the work with Iliashenko. Because that I think it's a paper, something that was done in the late 70s by Iliashenko and company, that were studying foliations, polynomial foliations, on C2. And not every polynomial foliations, but the generic polynomial foliations on C2. And for those generic polynomial foliations, you always have a line at infinity, which is invariant, with generic again. So if this has degree D, it will have, I think, D plus 1 singularities. And what the Iliashenko, Iliashenko and school proved, for instance, that the holonomy representation of the line at infinity I don't know why I'm writing like this. Just. diff C0, sorry. They could say, prove results about this representation and that it would be very complicated and so on. And exploiting the dynamics of this representation, they were able to show that if I take a generic foliation on C2, a generic polynomial vector field on C2, it induces a foliation such that every leaf, apart from the leaf of infinity, is dense. That any measurable set of leaves has zero or this total Lebesgue measure. This is what we usually call ergodicity. And there is also this quite intriguing result of rigidity showing that two foliations which were conjugated by a homeo are automatically conjugated by a very special holomorphic transformation, homeo close to the identity. Okay? So we had these results. But you see this kind of result, when I first saw and when we first studied, did not pertain to the theory of holomorphic foliations. This was not dealing with foliations on P2. For us, foliations having an invariant line is just a small set. So this has nothing to do with the generic behavior of a generic foliation on P2. It's a generic behavior of generic foliation on C2, which they're not the same topology. We count the degree differently when you look then from the affine perspective or from the projective perspective. And it was a major thing to be able to cross this barrier, to transform this result on actual results about the dynamic of general foliation on P2 or other surface. And Julio and Frank did exactly that. And they did not only that. There's another aspect of their statement. Because they could break this barrier and prove the results for an open set of foliations on P2, not a generic one, as probably Bertrand will explain for you tomorrow. But they could prove the existence of an open set of foliations on Pn, not only on P2, on Pn, having the analog behavior of minimality, ergodicity, and rigidity. But also a thing that I like very much about this statement is that they not only took the time to break, after having broken the barrier in dimension 2, they took the time to state it in a correct level of generality and do it not only for P2, but for Pn. I think that these are two very important contributions in the sense that they really broke the kind of statement that we were being done at that time. I think this is really something. And so the statement is this. So there is this there. So we have the space of foliations of dimension 1, or let's say on P2, and of degree D with D at least 2. Let's discuss the case D equal 2, for instance. All right, so this thing is dimension 14. It's an open in a P14. The open conditions, this is just the projectivization of H0, P2, omega 1, P2, 4, minus 1 forms with codimension 1 zeros. That's why it's open here, but you have this. Inside of this thing, you have a hypersurface, P14. I know that's 14 because that's the only dimension where you can produce foliation with prescribed singular set, and by the result discussed yesterday, you essentially have 1 for each singular set, and we know that in degree 2 there are d squared plus d plus 1 with 7 singularities, Each singularities are 2 parameters because we are on P2, so it's P14. And here you have a codimension 1, a divisor, codimension 1, corresponding to the foliations have a invariant line. And on this set, we know that there is a set of total Lebesgue measure, a dense and generic set, where the theorem of Foliations applies. Right? But you don't know nothing about the behavior of the foliations nearby. And what we do know is that away from the set, there is an open, a real Zariski open, where foliations have no algebraic leaves at all. But what's the structure? We don't. And what Frank and Julio were able to do is to take for almost every point here, where you are going to have a leaf at infinity invariant and generic holonomy group, they could produce open around this point, if I understood correctly, such that the foliations here are like that. Okay? So again, there is this component of the result that it becomes a problem of the dynamics of diffil. So diffils of Cn0, where states here. So let's say that we have d elements of diff Cn fixed in the origin, and suppose that their linear parts generate a dense subgroup of Gl and C. Then there are constant epsilon r, such that any transformation G1, Gd, approximating F1, Fd, but now they do not necessarily fix the origin. They generate a minimal and ergodic pseudogroup either on this ball or on the ball minus a common fixed point for all of them. I believe that Julio will discuss some of the kind of techniques that go into the proof of this result. Is this construction of flows inside the closure of these pseudogroups using Zassenhaus lemma and things like that. And so I will not spend a lot of time trying to explain, because there are people much more competent than I here to do, but this is another result I'm very fond, and I think it's great reading if you haven't took a look at this paper. It's really important paper in the subject, I think. And also, I think it inspired a part of work of Bertrand. There is a breakthrough in this line of investigation, very recent, where they proved that this rigidity that we saw and we were kind of looking at everywhere from the work of since the work of Iliashenko, indeed, it's not everywhere. There are foliations which are topologically rigid. You deform a bit, John Ulu foliation in degree 2, that's a result of Bertrand and Aurélien Álvares. You deform it a bit, it's still the same topologically. Okay? So that's what I want to talk about this result. And so I'm moving toward the third result. And who wants to guess? No? Someone? That was easy, right? I was kind of obliged to talk about this result. And also, if you see, there was a logic behind. So the first paper was written, this I'm guessing, right? As all mathematicians, when we do history of mathematics, we put our fantasy to work and do guesses. So the first paper was done where? In Rennes. That was the picture. The second was done part in Rio and Lille. What's missing? Where Frank was traveling around? Barcelona. So the next paper was written down at least. I don't think it was conceived there, but I know for a fact, he told me about the time that he wrote most of it while in Barcelona. And it's the preparation theorem. So this is a very beautiful work with really great ideas and new ideas, very different from what was being practiced at the time. So let's go straight to the statement. Perhaps right here, because there is a lot on this blackboard, on this slide. So we have Cn plus 1 with coordinates z, and here there will be a lot of z, z1, z2, zn, and w. And we are going to take, or he is going to consider, n is at least 1, and he's going to consider a one-form theta, which is f1 z w dz1 plus fn z w dzn plus g z w dw. So as you expect, f1, fn, g functions or convergent functions in zw, defining a codimensional one foliation, meaning that this form is integrable. And he's assuming that there are no common factor among this form, as we usually do. And his theorem is the following, saying that assuming that GW, the assumption is that the GW, that the order in W of this thing is K, then we can do a kind of Weierstrass preparation for one forms, can change the coordinate W in that way, so that the foliation becomes polynomial in W. In principle, it was just a convergent power series in the whole variables, and he just killed infinitely many terms in n plus 1 terms to guarantee that this all becomes polynomials in W. Okay? Perhaps it's hard to see the relevance in stating like that, or if you are familiar with, if you spend some time studying the structure of analytic sets following the classical approach where you use Weierstrass theorem to do everything, you see that this is relevant. But here, I think it's perhaps easier to grasp in this particular case. So let's start with a germ of analytic vector field such that the linear part is nilpotent. So you see the linear part is y ddx. There is no term on ddy. And what I'm saying? Then just the order. Assume that linear part's not right. But here is more general. But we are just he's just assumed that the linear part is not radial. But I think that it's more relevant, or perhaps more, easier to grasp. Let's just think that it's nilpotent. Then there exists a change of coordinates such that you kill completely the dependence of y except in degree 1. You keep only degree 1 on y and has nothing more. Result like this, I was talking about nilpotent, result like this was already known. It was proved by Stroessner and Zolodek in this paper. I don't know if you all remember that we used to have this category of papers in mathematical reviews, that the paper that were considered important by the editors of mathematical reviews received this label feature review, where the reviewers say that a lot of things, blah, 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 and then this is a deep and relevant result in the field, and the reviewer was our friend Loray, so it's a paper from 2002. The point is that this was really a tour de force. It was something that was known. The previous result in the nilpotent case was known by Takens formally, and they were able to prove convergence. And it was really, really painful proof. This very delicate and cautious analysis to control an iterative process like the ones Danielle was explaining early today for us. But analysis, right? Analysis and hard analysis, estimations, control, right? But his proof, the proof of Frank, is geometry, pure geometry, no analysis at all, not a single bit of analysis, no estimation. Every time there was an inequality, 0 was in one of the sides, no analysis by definition. And it's very, very beautiful argument. So the idea is that it's really, really simple. It's incredibly simple. And yet very, very powerful. So the idea is to start with a local object, right? And you want to find the polynomial dependence in one of the factors, in one of the variables, in one of the directions. And so the idea is to proceed by a gluing construction, a geometric construction, and construct a semi-global object that will extend the original one. So from his local data, that's pictured here, he will produce, so this is only on Cn times C, or a disk times a disk. He's going to produce something that's on a disk times P1. He will globalize one of the directions. So essentially, it's just, by the definition of foliation, you have local triviality, and with a bit of thought and courage, you can realize that here there will be an annulus where your foliation will be essentially trivial, and you can just glue the trivial foliation to it. And by doing that, he had something which was local and become local on dn times d and become local in dn times p1. But now we can just, we understand foliations on dn times p1. And if we just try to understand what's a foliation on dn times p1, you easily see that the dependence on the variable of p1, on the coordinate of p1, is polynomial, because it's global. It's global on that factor. And that's it. 50 pages of analysis into 2 paragraphs of geometry. It's incredible. It's really, really an amazing result. And I think he had, it's one of the characteristics of Frank that always trying to understand things geometrically. He always starts something with a big picture, at least 3 colors. And the same approach after was used in another works. For instance, in his work with Michael to construct neighborhoods of curves without functions, and I think also had a lot of this kind of mindset, had a lot of influence in his work with Voronin and Teyssier, where they give a classification of neighborhoods of elliptic curves with trivial normal bundle or numerical or torsion normal bundle, and so on. So that's what I want to share. I still have some time, but I think we can open the floor for questions and comments. If you really want, I can try to make a bonus paper, but I don't think. Thank you.